Okay, so welcome to Lecture 3, which is entitled Continuity. And so this is now an extension to the work that you learned last year for continuity of single variable functions, but now extended in terms of how we look at continuity for multivariable functions, specifically two variables. So this material is covered in section 15.2 of the text. The objectives are to establish the continuity or discontinuity of a function, and the concepts and definitions are the continuity definition and the continuity of composite functions definition. So these are basically the main things, and then we'll have some examples as well. And as usual, the second slide is just an outline of the specific topics we'll cover, and so I'll just skip over this slide. All right, we'll start with the definition, and everything basically comes back usually to a definition. So we define the function f to be continuous at a given point ab, provided all of the following three rules are satisfied. First, that f is defined at ab. Second, that the limit xy approaching ab of the function fxy exists. And thirdly, that the limit of fxy as xy approaches ab is in fact the function f evaluated at ab. All three conditions must be satisfied. So the problem-solving strategy is as follows. First, determine if the given function is continuous at points other than boundary points within the domain. So we know that polynomials and rational functions are continuous at all points. Trig, log, and x functions are continuous within their domain, excluding any boundary points. So for instance, a log function, you basically would have to make sure that the argument is greater than 0, otherwise it has no meaning. And then we determine the continuity at boundary points of the domain, and here we need to verify that all three rules for continuity are satisfied, or alternatively show that one rule is not satisfied, in which case the function is not continuous. So in this slide, we give example functions with special properties, specifically properties regarding the existence condition. And I've highlighted two in particular. We'll just go to look at each one in turn. So the sine function basically toggles between -1 and 1 at x equals 0. We actually define it typically to be x equals 0. The value of sine x to be 0 at x equals 0. And similarly, we have something called the Heaviside function or unit step function that toggles between 0 and 1. And again, at x equals 0, we assign a value of 1/2. So it's halfway between 1 and 0. Now, typically these functions are sine 0 for the sine and 1/2 for the Heaviside because they are used in a number of applications. And in particular, if we look at the Heaviside function, right, if you take its derivative, we end up with something that is referred to as a Dirac delta distribution, which we'll be discussing a little bit later in the course. It's very useful in terms of solving a wide range of problems. Now, we also have functions that look very similar to the sine x and Heaviside function. The one in yellow, x divided by the absolute value of x, looks very similar to the sine x, but in this case, at x equals 0, the function is not defined. Similarly, the Heaviside function has an analog, which is 1/2 times 1 plus x over absolute value of x, and again, at x equals 0, the function is not defined. And then we have a wide range of other well-known functions, such as tan x, square root of x, ln x, and 1 divided by x to the power of n being greater than 0. So for tan x, we know that there are specific values of x where the function blows up. Square root of x, we know that for values of x less than 0, square root is not defined in terms of it being a real number. For ln x, we know that x must be greater than 0. And for 1 divided by x to some power of n being greater than 0, we know that the function is not defined at x equals 0. There are many other functions out there which exhibit certain properties, but these are the most common ones. So basically, it's useful to have as a reference. It's not that you have to memorize it. It's just that we'll make reference to some of these functions at various points throughout the course. All right, so let's work through an example. You're given the following function, right? That is 3xy squared divided by x squared plus y to the power 4, as long as we don't consider the point xy equals 0, 0. On the other hand, to make sure that the function actually has a value at the value 0, 0, in this particular example, we're imposing the condition that it take on the value 0. Right? It doesn't have to, but we've done it for this particular example. So we need to determine the domain of the function. So 3xy squared over x squared plus y fourth. We're okay as long as x does not equal y does not equal, x does not equal 0, y does not equal to 0. Otherwise, all other values of x and y are acceptable. Now, the range on this function is between minus 3/2 and 3/2. We will show this to be the case later. For the time being, just assume that it is the case. All right. We note that 0, 0 is a boundary point of the domain of 3xy squared divided by x squared to y plus y to the fourth. All right, and so more or less, basically, that's what we're starting with. I've shown a little diagram on the right, which essentially shows the domain in the xy plane. Everything is acceptable except the origin, that is 0, 0, as indicated with a blue dot. All right, so let's go through now and determine if the function is continuous. First thing to do is to establish continuity of 3xy squared divided by x squared plus y to the power 4 in its domain, that is for x and y not equal to 0, 0. All right, 3xy squared over x squared plus y fourth is a rational function, so it is continuous at all points in its domain. You just have to make that statement. It's understood that rational functions basically will be continuous, and so therefore we can move on to the next step. All right, second thing is to establish continuity at the boundary point AB. So question 1 would be, is rule 1 from the definition of continuity satisfied? Yes, it is, because fxy is defined at the point AB 0, 0. That is, its value is equal to 0. So that's one check mark. Now question 2 is rule 2 from the definition of continuity satisfied? All right, so here we don't know, so we're going to make the assumption that the limit does not exist, which means we're going to apply the two-path test, which in fact is a contrapositive proof. So z equals the limit of xy approaching 0, 0 of 3xy squared divided by x squared plus y to the power 4. Here we basically look at the order of the numerator and the denominator. And so the suggestion is that we let x equals my squared. M will determine basically a particular path in the xy domain. Choose the value of m to be different, you have a different path. Now if you look at my squared, on the numerator you're going to have order of 4, and on the denominator you're also going to have order 4. So that's perfect because we'll get cancellations taking place. So we just make the substitution here. You can see x is basically substitute with my squared, and the additional y squared gives you the y to the fourth power. And on the denominator term, you end up with y to the fourth being common to both terms. Y to the fourth basically get canceled from numerator and denominator, and you're left with this expression here. Well, by choosing different values of m, you're choosing different paths, which means that the value of z depends on the chosen value of m, meaning the chosen path, which means effectively the limit does not exist. Now, you do not have to go on to rule 3, because if any one of the rules is not satisfied, then the limit does not exist. So we stop at that point. Just as sort of out of curiosity, if we had reframed the problem as z is fxy equals 3xy squared divided by x squared plus y to the fourth, right, without basically imposing a condition at xy equals 0, 0, then the function does not exist at the boundary point 0, 0, and thus by rule 1 of the function is not continuous. Okay, so this now goes back to a comment I made earlier about the range of the function. How do we determine what the range is? Well, the maximum and minimum of z can be obtained by first determining the maximum minimum of the function 3xy squared divided by x squared plus y to the fourth, excluding the boundary point, and then determining the maximum minimum at the boundary point by computing the minimum and maximum of 3m divided by m squared plus 1. All right, the global minimum and maximum for z are located at the boundary point. So if you, for instance, were to determine the minimum of this function, you would find out that or minimum and maximum, then you can apply the first derivative test and set it to 0, and you'll find out that you'll get a maximum when m equals 1, which turns out to give you a z of 3/2, and you'll get a value of m equals -1, which is a local minimum, which gives you a value of z equal to -3/2. And so that would be a simple way to determine what the range is. So range exists between those two values of z. All right, so the path is x equals my squared, and we have basically here an interactive program that you can play with to check to see how the path changes as you change the value of m. So this is an example where m was set to 1 and the value of z turned out to be 1.5. Here's a picture of the function itself. Again, showing m equals 1 shows you the value of z, which is the blue line, which is right at the peak. That gives you a value of z equal to 3/2. And the path in the xy domain, which is the x equals my squared for the value of m, is the green line that you see here. So the blue is the actual functional value, and the other one is basically the actual path in the xy domain. All right, here's some more pictures sort of showing you different paths, m equals 1, m equals -1, and then various paths in between. And so you can see over here, this is for m equals 1, this is where you are for z, and this is the value of x equals y squared. That is when m is set for 1. In this case, it's -1, so that means the parabola is in the opposite direction, in the negative direction. And this is the value for z, which is at constant value of z equals -3/2. All right, so next thing is to look at the continuity of composite functions and see whether or not there's a technique that we can use to determine the limit for these functions. So the theorem states that if you're given u as a function of xy is continuous at ab, and z is a function of u, and it's continuous at g of a of b, then the composite function z of f evaluated gxy is continuous at ab. So the example we'll use to just illustrate this theorem is the one that's shown here. We say that z is ln of x squared plus y squared plus 4. And so x squared plus y squared plus 4 represents the function g of xy, right? And that argument of the ln function basically will become u, all right? So we set u to be that value. So we need to know, how does z equals ln u behave, and how does x squared plus y squared plus 4 behave, all right? So let's look at g of xy first. We notice that it's continuous for all xy in R2 since it is a polynomial function. So that's good, it's continuous. The function f of u is continuous as long as u is greater than 0. Don't forget, ln of u only is valid if the argument is greater than 0. But u is equal to x squared plus y squared plus 4. And no matter what values of x and y you put in there, the value of u will always be greater than 0. In fact, it'll be greater than or equal to 4. And therefore, because in both conditions are satisfied, that means z equals fu is also continuous for all points in real numbers in the 2D plane. All right, so we'll do one example here. This, again, is sort of an interesting one. Determine the points at which the function z is equal to sine x squared y over x squared y. If x squared y not equal to 0, and 1 if x squared equals y equals 0 is continuous. Okay, so how do we go about doing it? Well, you'll notice that on the numerator and denominator, x squared y is common. So let's give it basically a variable name u. So gxy would become x squared y, and x squared y as a whole basically would be replaced by u. And so that's basically what I've done. F of u now, right, becomes, or z, f of u is equal to sine u over u if u is not equal to 0, and it's 1 if u equals 0. And u equals gxy equals x squared y. So we know the function gxy is continuous for all x and y. It's a rational function. So there's one thing that basically we now know. And the function f of u is continuous at all points within its domain, but at boundary point exists at u equals 0. All right, now that we're dealing with only a single variable function, you can use all of the techniques that you developed in the first year Calc and Calc 2 classes to determine if the limit exists. And so in this case, it sort of seems to be useful to apply L'Hopital's rule to determine what the limit is. And so if you have something of a numerator and a denominator, where basically you end up basically with a 0 over 0 type of arrangement, then you take the derivative of the numerator with respect to u, and you divide it by the derivative of the denominator with respect to u. So if you take the derivative of sine u, you get cos u. If you take the derivative of u, you get 1. And the limit of u approaching 0 would be cos of 0, which would be equal to 1. So the limit basically does exist. So basically we can say that rules 1, 3 are satisfied. Therefore, f as a function of u is continuous at all points. Hence it follows that z is continuous at all points of R2, which is xy, in the xy domain. If you want to look at the function, you can. Here's the link. This is just a simple picture showing what it looks like. You can look at it and rotate it and do whatever you want with it. Anyway, this concludes lecture 3. Thank you for listening.